So, what exactly is digital twin? Imagine a virtual replica, a dynamic digital model of a physical object, system, or process. This isn't just a static blueprint, it's a dynamic digital model that's continuously updated with real world data, allowing for analysis, prediction, and optimization. Digital twins are already revolutionizing various industries. Think of manufacturing, where we monitor factory operations to improve efficiency and identify faults. In urban planning, they guide the designer to design smarter cities. Even in healthcare, they simulate patient models for surgical planning. Recent advances in deep learning and computer vision have made digital twins more powerful and adaptive by enabling real-time visual interpretation, prediction, and decision-making in complex environments. When it comes to wireless communication, digital twins are being explored to optimize communication infrastructure. They can predict network conditions, detect failures, and adapt proactively, leading to more reliable, intelligent, and low-latency communications. Migrating to millimeter wave and terahertz networks improve vehicular communication capacity, but introduce reliability issues due to their strong line-of-sight dependence. Blockages cause connection drops and delays when switching roadside units, as this requires scanning many narrow beams. Digital twins are being explored to address these challenges in 5G and beyond. Therefore, we propose a novel end-to-end framework that leverages a digital twin-assisted communication strategy to predict potential blockages in advance and proactively perform handoffs between roadside units, effectively minimizing outages, enhancing the stability and reliability of vehicular communication. Here's our proposed architecture, which consists of 5 key components, namely environment sensing, digital twin construction, digital twin initiation, blockage prediction, and at last, RSU selection. First, environment sensing is achieved through multiple cameras and RTK GPS modules to gather visual and locational data of communication vehicles and potential blockages. Next, in the digital twin construction phase, object detection is performed using a pre-trained YOLO version 10 model. Simultaneously, depth maps are estimated using Depth Anything version 2 to precisely locate each object in relative 3D space. We utilize the GPS coordinates of communicating vehicles to locate them within the image space using an algorithm based on projective transformation. These features are then fused to create a rich, L-dimensional embedding for each entity in our digital twin, representing the current state of the environment in a latent space. This is the initialized digital twin in an L-dimensional vector space, continuously updated in real time based on environmental sensing. Now, crafted feature embeddings are used in the blockage prediction module, where our custom-built transformer model, trained on Unity simulated datasets, predict future blockages. Finally, a partially observable Markov decision process-based algorithm is employed for RSU selection and proactive handoff, enabling optimal switching between roadside units based on predicted blockages. To train, validate, and evaluate our model and framework, we developed a dynamic simulation environment using the Unity game engine. Within this environment, we generated a synthetic dataset tailored to our experimental objectives. So, how does our system perform? Here, we have evaluated our full framework using simulated data from the Unity simulation environment in here. As you can see, these simulations clearly demonstrate how our system detects blockages and switch the connections proactively in dynamic and complex scenarios. These heat maps for multiple communication vehicles show movement within bounding boxes. providing spatiotemporal insights and extracting depth features to analyze dynamic behavior. Our blockage prediction model showed significant improvement in F1 score and recall after transfer learning from synthesized data from Unity. This outage probability plot demonstrates true potential of our framework with respect to the conventional method. Our framework combines a digital twin with intelligent decision-making for proactive RSU handoffs. Using real-time visual and position data, it predicts signal blockages from static and dynamic objects. This end-to-end system integrates user tracking, blockage prediction, and handoff management, offering a scalable, real-time solution for next-generation vehicular networks. In future work, we aim to construct our vision-based digital twin to capture more complex and semantically rich environmental dynamics. We plan to apply a partially observable Markov decision process (POMDP) framework to optimize proactive handoff decisions under uncertainty, striking a balance between maintaining high link quality and minimizing handoff costs. Additionally, we will develop a scalable, end-to-end system that integrates real-time user tracking, blockage prediction, and proactive handoff management for multiple users in dynamic environments. Thank you for watching.